So, unless anybody's like wildly opposed, I suggest we look at a bunch of these things on Desmos together as a class first. Okay, so you guys have some experience with Desmos stuff, and I don't know how much experience truly you have, but all I'm going to do is I'm going to minimize this so that I can drag it to fit the screen so that if you're watching this later, you can see the same stuff that I'm seeing. All right, so I hate the way that my screen just tries to click right to what I'm doing, but that should show everything. So check it out. I'm going to put in our function. So here's sine, and it wants me to use x. I will use x here. There's a graph of sine. Now, if I put an a equals, or if I do something like this, if I put an a here, it's going to ask me, would you like to make this a slider? Do you guys know what it's asking me to do?
So you can like change it back.
Yeah, so check it out. I'm sliding it. Okay, we are going to look at d plus or minus, and we'll just let the minus work its way out, bx minus c. And I want all those to be sliders. So real quickly, let's just think. I don't want to change that one yet. B I want as 1. C I don't want to exist yet. So I'm just going to set it at 0. And A is 1. Looking at this information that's on Desmos right now, on your page I want you to write down this expression, but only with the ones that matter. If it's 0, I don't think it matters. Just show me the function that we're actually looking at. If you have a variable that has a number, if it's 1, I wouldn't really necessarily bother including it. But we're going to see if we can't play around with all of these values and just kind of make sense of what happens with my function. So here's what I have right now. That's just the original sine function. I'm going to look at your page. You'll probably have a letter on it or not. We'll see. Good. If b is 1 and a is 1, we just have the regular old sine function. Do you guys agree with that? I like that, a sine bx. If you want to put it, I'm good with that, Riley. Now, we're going to try to generalize this as we go, and please let me know if it's feeling like crazy fast. Of all of these variables that I can possibly change, I'm going to just start with a. Let's just see what a changes. Before I start moving a around, do you guys have any idea what's going to happen? Say that again. When you say expand or condense, can you tell me what you mean by that? Okay, so maybe, as we're looking at it, you do not have to write this, but I want to make sure we can see that, hey, we've done this stuff before, and the same thing applies. You probably have a hard time at this point graphing sine theta or x or whatever in your head. Like, maybe not, because Kalisha hit it right off the bat, so it starts at 0 and then it waves. Cool. If I had some function f of x, and let's say that I'll just plug in numbers. F of 3 hypothetically was equal to 5. If I were to do 2 times f of 3, what do you think it would become? 10. You would just double it, right? They both multiply by 2. I know that that happens, which means if I use this logic and see that I know how it works with a regular function, and then we accept the fact that sine is also a regular function, we shouldn't see anything too crazy. A right here, if I make it bigger, like right now I know it goes to a maximum of 1, right? Wherever it is, it's not going to show it. Do it, do it, do it, do it, do it. Okay, I hate it. I still hate it. Why would it not show me the max? Oh, it's waiting for me right there. Okay, it did. I'm just blind. Okay, if I double this and make it a 2 for a instead, I now have y equals 2 sine x. Do you guys agree with that? Cool. Let's check it. Let's see if that is what happens. Did that do exactly that? Did it just make it taller or shorter? Is that what you meant by expand? Okay, so changing height. And we'll talk about why I wouldn't use the language expand, Barsega, but that's great. Okay, those of you in my fisheries class, we've talked about waves. We have components of waves that we talk about. What's the distance from here to here called? This is my wavelength. Now, in our problems, you might think of that as being the period instead, but it's the same idea. Okay, the very highest point of a wave, typically referred to as what? The crest. Not Riley or Huggins. Anybody know what the smallest part of the wave might be referred to as? It does not look like it's spelled normally. Trough. with a GH instead. It's a weird word. Okay. If I said how tall, like what's the height of this wave on the board, could you guys tell me? It's 4, right? Because from top to bottom, it's 4 units. Everybody cool with that? Now, that value of A isn't quite the height, but it's related. I know that that A value is 2 and the total height is 4. If I make the A value, I don't know, 4, what's the total height? 8. What if I make it 5? So how would you get A value if you knew how tall your wave was? It's half of it, right? So check it out. We are going to do this back and forth between Desmos and our notes. Starting today, this should be the last thing that you have, right? Cool. So here we go. We are going to be looking today and continuing on, and I like this dark red color. Let's talk about transforming parents. Or more simply put, transforms, weird, of sine x, or sine theta in our case, and cos theta. And all we're going to do is just make sure that, one, if you have questions and something that I say just doesn't make sense, let me know like immediately while we're looking at it. But we're going to try to go very little writing with this. First thing right off the bat, A. And it drives me crazy that it's not capitalized, but it doesn't show up capitalized. A is for amplitude. Right off the bat. That A value represents the amplitude of our wave. And super easy to define. We're just going to say underneath of this, and I have a lot of space, amplitude equals 1/2 of the height. If you need more specific stuff, we'll just say that the height is crest, the very top of our wave, to trough, the very bottom of our wave.
Every class is the same.
It's so weird how much overlap there is between them all. Constantly. A is for amplitude. Now, we can do one of two things. We can, for every single thing that we change, we can do like an example of how do we graph it by hand. I'm okay with that. Or we look and see what all these things impact, and then I'll show you the hollow way of doing it. Because I think it's a lot nicer if you do it like me, but that's totally biased because I like the way that I think. I assume for the most part you guys normally seem to like the way that I think about math because we do it all the same way. Let's do the second one unless anybody wants examples of each as we go. Okay, hypothetically, what if I make it negative? Like -2. Louder. I saw the consonant getting ready to come out. You went, and then you stopped. I assume that was an F. Or I'm way off. What do you guys think is going to happen if I go back to Desmos and I make this instead of a 5, I make it a -5? So shorter, maybe. Let's check. Ooh, if I get down to here, there it is, right? And then, it's been reflected over the axis, right? Just like we saw before. So, as I'm looking at this, we're going to make one little change. There's something about this. The amplitude, it doesn't make sense to have a negative height, right? So we'll just say that this is 1/2 the height. I'm fine with that. And then we'll make a follow-up. If A is negative, and I'm just going to write less than 0, we reflect. Reflect over which axis? I'm fine with calling it X. Alternatively, you may want to call it the theta axis, but we're probably going to wrap around using X again. Cool. Everybody cool with the amplitude? Let's let it ride for a minute. We'll see it. There it goes. And my amplitude is just constantly changing, and I get this wonderful, neat wave. Cool. What's A for? Amplitude. Awesome. So I'm going to go back to the standard where it's just 1, so it's our regular old sine function. And what are we going to look at next? Barsega, you get to pick. Do you want B or C or D? B. All right. This one does not work as nicely as my alliteration here, but here's what we're going to do. I'm going to come back here, B, and we're going to determine what it's for. here I am, and I'm going to change this to be trig stuff. So let's say I go from, I don't know, negative 4 pi to 4 pi. And let's jump by pi halves, because that's what we typically did. Did it let me do that? It did not. Why didn't it let me do that? You guys see it's not letting me, right?
It's labeling it.
That's what I'm, thank you. Pi, thanks. Cool. I don't really care about the y-axis, so I'm just going to keep it. Okay, notice here's all of our nice values that we saw on our graphs. 0, pi halves, and that guy, right? All of them are there. All right, as I change b, I want to check something out. What's changing about it? So the wavelength, certainly. So at 1, let's just look here. And this is weird because I can't adjust it the same way. Right now, how long does it take me to go through one whole sine wave? And by how long, I'm not referring to time. I'm talking about how many radians. 2 pi. So this is the piece that I could just pick up and copy and then set down and it repeats, right? Okay. If I make b bigger, like for example, I make it now this much bigger. 2. There we go. That value changes, right? And it's no longer super nice. But do you agree that that's the end of my first period? Is my period changed? What's the original period of sine? 2 pi. So when I do this, it's changed, right? How did the period change? Did it get bigger or smaller? It got way smaller. As I get this less than that, it gets less wavy, but that's still a wave, but the period's now huge, right? So I'm just changing the period of my function. So for this one is not as nice. B is for change in period. I really want to call it period just so it works, but I'm not going to. Okay. The rules that we're going to work this out by, and the way that I denote it is not exactly like your book does, but it works out nicely, I hope. We know that the normal parent function has a period of what? So here we go. The parent, and I'm just going to say parents, but we're only going to write one of them. Y equals 1 sine of, and this is going to look dumb for a second, but we're going to do it. Do you agree that's 1 theta? Like when we write sine of theta, it's really just 1 sine of 1 theta. Okay. We know that the parents, this thing, have period equal to, and you guys told me a second ago already, what's the period of sine and cosine? So before we write 2 pi, here's what I'm going to suggest. Is 2 pi really a fraction? Like, and it feels weird, but do you agree that it's this? 2 pi over 1. Okay. Now, if we look at this, and hypothetically, I made this 2 pi over 2. And let's see, we're good here. So if I change this to 2, and I look at 1 full period of sine, can you guys see where 1 full period is? It goes to pi. So if I make this sine of 2x, the period got cut in half, right? What if I make it sine of 4x? Instead of cutting in half, it should get cut in what? Into fourths. So do me a favor real quick. What's 2 pi divided by 4? It's pi halves, right? Notice what we have going on here. Here is 1 full period of sine. It goes up to here, up until pi halves. Which means that as we're generalizing, if the parents have this, then, yes, y equals sine of b theta, will have the period is equal to 2 pi divided by what? B. It's 1 normally because it's 1 theta, but I just saw that on each of these I just divide it by that number, and we get whatever b is, it's there. 2 pi over b. Okay. Now, as we're going further, we have a changing the amplitude, b changes the period. Just so we can look at it, and this is where that language beta is going to come in. If b is large, it makes the period smaller because you're dividing by something. So that'd be what I consider condensing my wave. I'd be expanding it out the other way if b is between 0 and 1. Okay, we will deal with all of these. Any questions there? Do you guys see that that's what's happening? Big B means smaller period, small b means larger period. Okay, so now if we let this one run, we're just going to see what it looks like. Here it is. It's like a string compressing and stretching out. It's almost like springs would perfectly be measured using functions like this or something. I don't know. Sounds harmonious to me. Cool. I know that's a weird word. It's because it's called harmonic motion. There was a point to it. Cool. All right. So let's make b 1 again. Sweet. So that's our parent function. What are we doing next, Abigail? D or C? C. All right. This one sounds ugly, and it might look ugly for just a second. C is for what is known as a phase shift. Okay, which we're going to define this in more specific language. The phase shift can be hard to think about, and we're going to do a little bit of inequality work right off the bat, and we're going to make sense of this. As I look at C, here's all I want to focus on. I'm going to zoom way in. It's going to, like, obviously each of these is going to change something about this, but as I change C, what does it look like I'm doing with my function? I'm literally just moving it left and right. So this is my horizontal transformation, if you want to use other language. In here, it's called a phase shift, and it happens for a very particular reason. Graphing these things, you could pick literally any point to start your table, and maybe it'll be nice, but the odds are against you that it will be really nice, unless you start at 0, which is what we did on the parent, right? Now, there are always going to be values of theta that spit out nice, easy to plot points. At 0, 1, -1, they're going to show up if you pick this correctly. So as we're looking at it, what I want us to really focus on is if here's my parent, normally the starting point, the leftmost of any period, and I would like to focus on this very first period because I think it's the nicest one. The left point is at 0, right? And the right point ends all the way over here, a whole period over. Okay, as we're looking at our phase shift, all that's changing is where does it start? So if I move it to 2, for example, and that's an ugly number, but notice it just starts at 2 instead of 0 for the x value. Have I lost you guys? Okay, so we're going to use this idea and see that, hey, we're just moving things left and right, and we're going to be able to make sense of this easily enough. Now, I'm actually going to move this whole thing up to the other side so I have room to write it. So C is for phase shift. And then I promise we're going to put it all together toward the end, and graphing these things is fairly tedious, but totally doable. All right, so C is for our phase shift. Here's a weird thing. Not super weird, but notable. The argument of, and we'll just do a nice one with an amplitude of 1 and no value of d. Do you want to do sine or cosine? Doesn't matter. We've been doing sine. You just want to roll with it? Okay. So I have the argument of this expression is, and I want you guys to tell me. What's the argument of that sine function up on the board right there? All right, so I hear whispers, but I don't hear words.
Bx minus c.
Love it. Everybody cool with bx minus c? Now, when we start to think about what this c value does to us, it's not on its own. The argument is bx minus c. Now, right off the bat, this changes the period. And I know that it changes the period because b is what changes the period, right? So I already know that there could possibly be a change in the period here. What we need to work out is how does the B and the C, how do they interact with one another to actually move my graph? Because it can be kind of complex. Good news, it's not. We can make it way simpler. Regular sine. Runs from theta equals 0 to theta equals, where does it end for the first period? 2 pi. Now, I'm going to go ahead and make one step further and just argue that maybe it's 2 pi over b in this situation. Because maybe I've shortened the period or not, but either way it starts at 0 there, right? Okay. Once we have this, we're going to be able to think about a little inequality here. Whatever my argument is, no matter what angle it is, I can find a coterminal angle that lives in the first period. So for example, 9 pi fourths is the same thing as pi fourths, because it's just 2 pi plus 1 more pi fourths. Are you guys cool with that? Which means for our functions then, our theta has to live between 0 and 2 pi. Now, in this situation, I used x right off the bat. Did you guys notice? I said x here and theta here. To be consistent, we need to decide, am I changing these thetas to x's so they match, or are we changing this x and this x to a theta? I might have said the same thing, but there's two options. Theta to x. Okay, so I'm going to change this theta and this theta to x, just so they match. Okay. Now, remember, what we're actually plugging into my function is the angle. So if I have bx minus c, that's what's going to give me the angle that we're plugging in. So whatever bx minus c is, I know that it's always going to be less than or equal, or greater than or equal to, to 0, and less than or equal to 2 pi over b. And I'll go 2 pi right now because we're working with the nice one. Every argument can be put somewhere between 0 and 2 pi, or within that period. First little check, yay, nay. That's because I can always make my coterminal stuff, right? Now, if I wanted to solve for x, could I? Like, it's a compound inequality. I want us to get just x in the middle here so we can see what winds up happening. What's the first thing that you would do? I'm going to add c, and this feels weird because I don't know how much like complex inequality stuff you've done, but instead of left and right, there's 3 pieces. I can add c to every piece, and it's the same thing. Cool, cool? Okay, we'll take little steps with the understanding that you might not. So I wind up with c is less than or equal to bx is less than or equal to 2 pi plus c. Haven't done anything too crazy. There's only one more little step to knock out here. What would you now do to solve for x? Every single piece gets divided by b. So this gets divided by b, and then I'm going to do it as everything gets divided by b. I'll write it like that. And this gets divided by b. Which means we now obtain, that's supposed to be a b. B. Means that I now know that, well, c over b is less than or equal to x is less than or equal to 2 pi over b plus c over b. Okay. It probably feels like we're just doing some manipulation stuff, and we are, but let's check out what really happened just now. Normally, I start at 0, yeah? Like, that's where my function normally starts. This thing has adjusted for the period right off the bat, and it's adjusted for this shift. So all I see now is that instead of going from 0 to 2 pi, I'm just going to go from this point as my first x value instead of 0, and then this will be the last one that I plug in. Okay, it looks gross, but in practice, this works really nicely. I'm going to make one more really important note. This is the starting point of your table. Now, if we ensure that that's where our table starts at, it ensures then that we're going to get a nice value that our function spits out at us. Okay. Other little pieces here. This is the right endpoint, all of it, right here. Last point on table. And we only have one more little piece to decide. We're going to get there. You do not have to circle this one, but what is this again? What's the importance of that? We've seen it elsewhere. That's the period of this function. So notice we're just saying, hey, start here and then go one full period past c over b, which is exactly what our function should do because it's periodic. All right. Last little letter. We saw that C shifts this thing, and I'll go here just in case people aren't quite there. C moves me left and right in combination with B. A makes me taller or shorter or flips it completely over the axis. That's my amplitude. B dictates the period of this function. Easy. What's the only thing we haven't dealt with? D. This one is going to be the least of all that we write with. If I have a function x squared, and I now want you to graph, let's say this is f of x. And like, you don't have to physically graph this. Do you guys know what it looks like? I don't believe you. Talk with your neighbors, brainstorm. What does a graph of x squared look like? Throw up your hands when you think you know. Right? It's just a parabola. It's an upward opening parabola. You might not have remembered, but I think you did know that. Cool. What if I did this? So we'll say g of x instead equals 3 plus f of x. So now that's x squared plus 3, or 3 plus x squared. How would that move my parabola? Here it is. If I add 3, what's it do? We raise it up, right? Or if I minus 5, what's it do? Brings it down. What do you think the d value of our d plus sine x does? Up and down. So instead of a horizontal transformation or translation, we instead get a vertical transformation. So last little section. I wish I had used k because that's what we normally use. D changes vertical location. Okay. Do I need to say any more about that one? It's a vertical shift, and I'll show you on here. That's all D does. So, hey, let's move it up 2, means that instead of going to 1 as a maximum, what do you think goes to now? I know that the sine of theta goes up to a maximum of 1. What if I shift the whole thing up 2 values? What's the maximum value now? And if the minimum value was negative 1, and I moved it up 2, what's the minimum value now? 1? Like I just added 2 everywhere, right? Okay. There's a lot of information up on the board right now. Feels okay, feels awful. You won't really have a good feel until we try to graph one. Here's my last little piece, and it doesn't fit in with these. When I graph these functions, I always do it in the exact same way every time. And it doesn't really matter whether I'm graphing sine, cosine, tangent, cosecant, whatever it is. I follow like the same process over and over and over. So you will definitely not find this in your book. But let's zoom in first of all. If I had written your book, you would. Here we go, big idea. When graphing, you may not need to do every single step, but when graphing trig, here's my suggestion. Do this, and we're going to sort this out. So let's do one together, and while we graph the function, and we're actually going through it, we'll define our steps so that we're doing them simultaneously. So here we go, steps, and then an example with it. Cool. So let's see if we can't make one up that's kind of ugly, but not like the worst function ever made. And I'm going to actually use your book so I don't make one that's awful or too easy, but it's on par with the rest of the stuff that you've done. All right. Well, that one looks cool. All right. We're going to graph an ugly one. We are going to graph f of x equals, love it. I want 4 times the cosine of x plus pi fourths plus 3. And it looks nasty. It looks terrible. Okay. Again, the steps that we list out, you are going to tweak them. The order that I'm doing them in aren't super duper important. I'll specify the ones that are. Right off the bat, at least when we're beginning, step 1, I would say let's identify or ID A, B, C, and D. And I'm going to take that and I'm going to move it down so that it aligns with what we're doing over on the other side. Okay, take a moment with your neighbors, let's say 30 seconds. I want you to identify A, B, C, and D. Let's check. Fern, what do you get for A? Okay, follow-up question. What impact is the fact that that's a 4 going to have on the graph? Good, so amplitude specifically, but you're right. Instead of my function now only going up 1 in its peak, it goes up 4. So it's much taller of a graph. Now it also falls down further as well, but I'm fine with that. Okay, what is B in this one, Makisha? What is B? I think you might have answered, but I might have misunderstood. And then remember that these are the functions that we're graphing, so I'll steal one of these real quick. And I'm using x instead of theta, but that is interchangeable. So here's what we had written the other day. What's B in this problem? What's connected to my x? So you're right. So we're using x here instead of theta. What's a number in front of x? Okay. B in this problem is exactly 1. Now, the reason that we care about that is I'm going to use that to calculate out the period here in a second. I don't think the period has changed. It's still a period of 2 pi right now. Okay. What about C in this one? Let's see here. Oh, look at that. Abigail, C for last name. I'm not going to say it because it's YouTube. Say it again. Negative pi fourths. Love it. Why not positive? Good. X minus C changes to x minus a negative pi fourths to make it change to the plus. And we've seen that before. It's like if I had x minus 2 in parentheses and I squared, C is really positive 2 and it moves it 2 to the right. It's that counterintuitive idea. All right. Last one, D for JV, because he's D-man. 3. And what impact is that going to have? It's going to change, don't say height. Cool. So instead of being at 0 centered, it's just been moved up 3 units. Okay. Is that part doable? Pay attention to C and that weirdness that happens with the sign, and we're golden. So check it out. Once you've identified these, and I don't honestly really care if you physically write it. I think it's helpful for the first few. I'm going to put a distinguishing thing on mine just so I can tell the difference. Step 2. Determine period. And I'm going to say that's always 2 pi over b, so it'll remind us. And start point. Yep, we'll do start point. And this one's important, and you'll never see it referenced in the book, but it's a Holloway edition, the jump. Cool. So my start point, Huggins, will you go get me a drink of water?
Yeah.
Cool. The jump. We're going to see this here in a second. I want us to look back at our original functions, and I have them here. What was the original period of sine and cosine? 2 pi. Now to get 5 points on a piece of paper, how many cuts do you have to make? That's a weird question. If I do 5 cuts, check it out. I'm going to physically cut a piece of paper real quick. And I'm just going to pause it because they don't need to see it. Okay. If I make 1 cut, how many pieces does it cut it into? So, the hollow way of doing this, and I think that this is the best way, but if you don't like, you don't have to. Take your period, and you cut it into, you want it to be 5 points, so you cut it how many times? 4. If you take, for example, 2 pi, and you cut it into 4, that's pi halves, right? When I talk about the jump, notice what happens on our tables from the other day. If I cut 2 pi into fourths, I get pi halves. So every single time to get my next x value, or theta if you will, I'm just adding pi halves each time. Now, as my period changes, that number will change. But we have it. Okay. In this one, let's dig in. If I want to know the period of this function, it's going to, since it's sine or cosine, I'll say, okay, it's 2 pi over, what was b? How about on this particular problem, what's b? 1. So what's the period of our function? 2 pi. Okay. We then pick our start, and I'll write this on the other side of it as well. The start point, we did that compound inequality just a moment ago. 0 changed to something in our compound inequality. It's c over b, right? What is c in this problem? Negative pi fourths, and it's really over 1 equals negative pi fourths. Okay, we've just identified the very first x or theta value on our table. The rest of this is so easy so long as we can do this last part correctly. I also want my jump. We determined that the period was 2 pi, and I'm going to cut it into 5 pieces by doing how many slices? 4, which means on our table, what are we going to jump by? Pi halves. Okay. Anything crazy challenging yet? Cool. The good news, we are done with the hardest part of this. Like, we've done the hardest part of all this graph. Okay. Finally, and there's really probably 2 steps, but I could make it 1. 3, make table with info from our second step. So I'll just say from 2. Now, this part is easy to do, but it takes practice. Right off the bat, what did we just decide the very first value that I'm going to put in my function is? My start, if you will. One more time, because that was kind of quiet. What did we say we were going to start at on our table? Negative pi fourths. So, here's the part, and I can't stress this enough. If you get lost in this process, please ask right then and there. I'm making a 3 column so we can see it. I'm going to start at negative pi fourths. Okay. Before anything else, I can make my whole table. I know that I start at negative pi fourths, and I'm going to jump each time by how much?
A period.
So not a full period. Pi halves. So that's 2 pi fourths, right? So let's get our other 4 points real quick, and then we'll fill out this table. Negative pi fourths plus pi halves, or 2 pi fourths, I think is pi fourths. Everybody agree with that? Give me the other 3. I'm going to pause it. I'll come around. The other 3 values are what we're after. Okay, again, I'm going to add the same thing every time. pi fourths plus another 2 pi fourths, because I'm jumping by pi halves, I think it's 3 pi fourths.
What is B?
In this problem,
What does it represent?
it's a number in front of the variable. And it's going to why we care about it is it gives me the period. So all I'm doing is taking the period that we found, which was 2 pi in this case, and I'm cutting it 4 times. Everybody get 3 pi fourths? What's the next one? 5 pi fourths. And the last one?
How are you finding?
So as soon as I identify the jump here, all I'm doing is I'm just doing this over and over. Plus pi halves to get my next value. Pi halves. Again. Again. I'm just adding pi halves over and over because I know that the way that we've set this up, I like it when my function spits out 1 at me and 0 and -1. We're picking values that guarantee that's going to happen. Because I know that a quarter of the way through whatever the period is going to get me up to +1 in the sine or 0 in the cosine. Okay. All right. Big moment coming up here. As we deal with these, I never expect, outside of this first example, for you to physically calculate out every single one of these values. Because was there a pattern when we graphed sine the other day? Like it went 0 to 1 to 0 to -1 to 0 to 1 to, like it just keeps cycling, right? So let's do the first one and see what we get out of it. Now, anytime that we're doing this, remember, if you got goofed up earlier, this value goes in for this one. Now, you might show a ton of work, you might show very little. I'm going to say show as much as you need to get whatever I have here in a second. This becomes 4, I hate that color, 4 times the cosine of, what would we get in the inside now if I did negative pi fourths plus pi fourths? 0. And then there's still a +3, right? What's the cosine or the x value of 0 radians? It's 1. Your unit circle is going to start kicking in. So check it out. This becomes 4 times 1 plus 3. What's our value here? I heard it whispered. It's a 7. Okay. Now, the more practice that we get, these are going to fly through because I know that there's a pattern. I know that cosine starts at 1 and then it falls. Like, I know that this is what cosine looks like. Now, if you don't have that in your head yet, that's okay. Let's do one more point. If I plug in pi fourths, what does my argument become when I have pi fourths plus pi fourths?
3 pi.
Try again. 2 pi fourths, can that simplify? Pi halves. Plus 3 still, right?
When you jump then, why do you... It's
No, I think you probably have a good question.
I just guess I didn't realize that it starts at 1 pi. You start jumping from 1. You go 3, 5, 7.
So I'm adding pi halves because that's my period divided by 4.
Yeah, I see that.
Okay. So check it out. What's the cosine of pi halves? Here I am at pi halves radians. What's the x value? 0. Cool. This becomes 4 times 0 plus 3. I think it's 3, right? Okay. Here's my challenge for you. Without actually calculating it, we know that the original parent of cosine does this. That was weird. Why did it do that?
How does it become 0 again?
So if you check out your unit circle, here's pi halves radians. So here's 0 radians, here's pi halves. What's the x value or the cosine?
Yeah, x. Or 0.
Yeah, that's how it came 0.
Okay.
Cool. And we've picked these so that this is always either going to spit out a 0, a 1, or a -1 every time. Okay, this next one. I want you guys to do 3 pi fourths. And when you see a pattern, that was a what, a 3? When you see a pattern, I want you to let me know. I'm going to come check. But as soon as you notice a pattern, I bet you can do the other points without having to calculate anything. Do the third point for me. we now have this entire table completed. When you're graphing these, we need 2 periods. So the cool thing about this is we get to just pick whatever our jumps wind up going by. Now that I mean on the axis. I need to see all these values, right? So if I'm graphing 2 full periods, I'll make it fairly wide to begin with. And then here's all I need to do. I know that on my original, I just did 0, pi halves, pi, 3 pi halves, and that was just how I assigned my ticks. Here, I'm going to go a little bit different. I'm going to start at negative pi fourths. And then I know that if I go pi halves, I get to the first new x value, right? It's pi fourths. Every tick along the way is going to make this super nice to graph. So if you want to label them all, you can. This would be how many pi fourths for the next one? 3 pi fourths, 5 pi fourths, 7 pi fourths. Now, I'm not labeling them all. You could label them all if you want to. Now, what we have set up currently is this is where my 1 full period is going to run between those. And then any other periods that I want, I just have to pick it up and paste it down. So check it out. We have that x scale picked out, immediately determined by these. Easy to choose because they're all equally spaced. I'm going to be kind of lazy with the y-axis. I know that my function goes from 7 to negative 1, right? Check it out. Here's 7. 3 would be like here, and negative 1 would be about here. And I'm just eyeballing it, but we're just sketching. How did I pick those 3 numbers, 7, 3, and negative 1? Because they showed up on my y values, right? So as soon as we're here, this is super easy. I know that my first point at negative pi fourths was at 3. Just kidding, it's at 7. At the next point, it curves down and it goes to 3. And I only ever have to just line it up with the ticks. The next tick, it goes down to negative 1. Back up to 3. And back up to 7 pi fourths. My scale's not perfect, but does this kind of look like the parent did? Especially once we connect it. Check it out. Here is my first period of cosine. I am really struggling with this one. Does that look like a cosine to you? I mean, pretend it's smooth and curvy like I did on paper. And then if I wanted another period, do I know that it just keeps doing this? So I can already see that, hey, I can get another period for free off of this thing because I know exactly what it looks like. And I can graph the entire thing. Okay, here's what I want you to do tonight. We're going to do a bunch of time to practice this tomorrow. However, I'm going to change the due date. I don't even know if I put a due date on it. In the Google Classroom, there is an assignment. That's definitely not due the 9th because that doesn't make sense. As you're looking at these problems, I want you to spend like 10 minutes on this assignment tonight. Hard stop at 10 minutes. Tomorrow in class, we'll do a bunch more graphs. 10 minutes tonight, and then we'll have a ton of class time tomorrow to work through it so that I'm here to help if you have questions. How long tonight? I need to see evidence that you've worked for some 10 minutes tonight. Cool. Baller. That's class. Seems easy, seems hard.
Not that bad.
Okay, we'll get more practice tomorrow. I will fix these dates because it's not the 10th today. And I'll see you cool cats and kittens tomorrow, except for travelers maybe. I can't seem to get a consensus of when you guys are leaving.